Hello everybody, today we will be going over how a galvanic cell works. Okay, so to start off, we have one cell with a copper node and another cell with a zinc node. Okay, next we have liquids in each cell, and for the copper cell, for this example, we'll use copper sulfate, so CuSO4. And basically what happens is, if it's an ionic compound, which is a metal and a non-metal, what happens is if it's put into water and you stir it up, it becomes aqueous, or that means that it dissolves into its ions. So what happens is it turns into Cu plus 2 and SO4 minus 2. Now here we have the other side, which is the zinc side, which in this case, it's going to be in a liquid of zinc sulfate, which is ZnSO4. And this one's also going to be dissolved in water, so it's going to be aqueous. And again, it means that it splits into its ions of Zn plus 2 and SO4 minus 2. Okay, once we understand the simple setup of the galvanic cell, the next thing we'll be doing is talking about reduction and oxidation. So reduction means that it's a gain of electrons. So you gain electrons, while oxidation means that you lose electrons. So we're going to take a look at the cell, and we are going to determine which side is the side that's being reduced and which side is being oxidized. So to determine which side's being oxidized and which side's being reduced, we have to take a look at this chart. It's called the standard reduction potential chart. And right here, we see that copper has a higher standard reduction potential than zinc does. So therefore, copper is going to be the one that's being reduced, while zinc is going to be the one being oxidized. So now that we know that copper is being reduced, we can write it out as the copper plus 2 electrons will become copper metal, copper solid. And what this is basically saying is that as zinc, let's say this is a wire, and as the electrons move this way from the zinc, because copper is being reduced, so as the zinc gives away electrons and the copper starts to receive them, what will happen is the electrons will start to add up here, and the copper plus 2 ions, so like these right here, I'm sorry, this one got erased a little bit, will move up into the copper metal and start building up. And what happens is it's going to be like a little blob of copper solids right here at the where the point where the aqueous solution touches the copper metal. So now, since we understand how the copper side works, we're going to be talking about the zinc side. So the zinc is being oxidized here. So what's happening is the zinc, so Zn, will turn into Zn plus 2 electrons. And those 2 electrons that you see here are the electrons that move across into the copper cell. And what happens to the zinc is, as it loses electrons, it turns into Zn plus 2, it will start to break off of the zinc node, and it'll start to go into the aqueous solution because of the negative sulfate ions in the solution. So it's kind of like the reverse here, where copper starts to become, the copper node becomes bigger, the zinc node becomes smaller on this side. Once we understand the concept of reduction and oxidation, there's one more thing to make this galvanic cell actually work, and that is called the salt bridge up here. So the salt bridge, what it does is, let's say there's some type of ionic compound that's dissolved in water. So let's just say NaCl, or table salt, and it's dissolved in water, so it's aqueous. It turns into Na plus and Cl minus. And basically what happens is the Na plus and Cl minus are in these tubes, or in this tube. And what happens is it will move to either side. So it makes the whole entire thing electrically neutral, and it keeps the flow of electrons moving, so that completes the circuit of the galvanic cell. Once we understand how the galvanic cell works, we can calculate the amount of voltage that this specific cell produces. So to calculate the galvanic cell, what it is the E cell at standard conditions, which is at 1 mole of concentration and 25 degrees Celsius, is equal to the cathode minus the anode. So how can we determine cathode and anode? Oh, sorry, I missed the E there. How can we determine the cathode and anode? So in this case, the reduction is the cathode. So my professor told me it was like red cat, and the anode would be like an-ox. So in this case, oxidation, which is anode, which is zinc, we can come back here and we can look at negative 0.76. So it's negative 0.76. Oh, sorry. While the cathode, which is copper, is plus 0.34. So 0.34. Since it's minus, what happens here is that turns into an addition. So once we figured all this out, we can add and we will get a total voltage of 1.10 volts. And now this is how many volts in standard conditions. Now, what if we want a galvanic cell that's not in standard conditions? Now, if we want a galvanic cell that produces a voltage that is in non-standard conditions, we would use something called the Nernst equation, which I will be going over in another video. This is just one version of it. So in the next video, I will be going over how the Nernst equation works and the other versions of it. Since we've covered the galvanic cell, let's go take a look at the demonstration. Hello everybody, here we are outside, and here's the demonstration of the galvanic cell in action. And as you can see here, there's an internal resistance, so the voltage is a little bit lower, and also I had some errors making it. So the voltage is not 1.10, but it's actually 1.03, which is very, very close to how many volts it's actually supposed to produce. And this is the concept of how my cell works. It's just my cell is not at standard conditions, so it produces a little bit more voltage than this. In the next video, I will be talking about how to make the fuel for my repulsor, and I will also be going over my development of my repulsor for the Iron Man suit. And thank you everyone for watching this video, and please like and subscribe, and goodbye.